Hello, we are looking at Unijunction transistor UJT. Welcome to Decreations Resources. Previously, we have seen what exactly a UJT is, how its basic construction is, and what its equivalent circuit is. We've also looked at the concept of intrinsic standoff ratio. Now let us understand how a UJT operates, or how is the working of a UJT. So if you consider or if you recall the equivalent circuit of UJT or unijunction transistor, now you can consider the equivalent current of UJT with the voltage source VEE. So this VEE is connected across the emitter and the base 1 terminal, and VBB is connected across the base terminals VB1 and VB2. So two voltages, VEE and VBB. And it's easy to remember. Whatever is connected between or whatever is measured across the base terminals B1 and B2 is VBB. And the other one measured between emitter and base 1 is VEE. Now we have already seen how there is a PN junction here. So let us denote that as an emitter diode, and it is reverse biased by a voltage drop across the resistance RB1. Let me repeat. We are looking at the voltage sources VEE and VBB, and now if you imagine the emitter diode, initially it is going to be reverse biased by a voltage drop across the resistance RB1 and its own barrier potential VD. If you recall, the voltage drop across the resistance RB1 is equal to neta into VBB, when neta is the intrinsic standoff ratio. So now the total reverse bias voltage across a diode will be given as the sum of neta VBB and VD. Or in other words, if we denote it as say VP, we will say VP is equal to neta VBB plus VD. Now as long as the applied emitter voltage is below the total reverse bias voltage, that is the right side of this equation, the diode is going to remain reverse biased and there will be no emitter current. However, as the applied emitter voltage reaches or basically exceeds the value equal to neta VBB plus VD, that is the right hand side of this equation, the diode starts conducting and the emitter current starts flowing. The value of emitter voltage which causes the diode to conduct is called the peak point voltage, which we have been denoting as VP. So we just mentioned that VP is neta VBB plus VD. Now as the emitter voltage reaches the peak point voltage, the diode conducts. So obviously when you say diode conducts, that means it has become forward biased and the emitter current begins to flow. Now under this condition, the unijunction transistor is said to be fired. So the word used is the UJT is fired or UJT is triggered, or in simple terms you can also say UJT is turned on. Now at this particular instant, the holes from the p-type emitter region are injected into the base region and are swept by the electric field towards the base terminal B1. The presence of excess holes slightly reduces the resistance RB1, which in turn reduces the intrinsic standoff voltage, which if you recall is neta into VBB. Now this action is also called conductivity modulation because the conductivity of the material between the emitter and the base of terminals increases as the holes are injected into it. It's obviously a regenerative process because a smaller value of intrinsic standoff voltage results in a stronger forward bias across the diode. Now, due to this, more holes are injected and the intrinsic standoff ratio into the voltage VBB, that means the intrinsic standoff voltage, neta into VBB, it is further reduced. As a result of this, the emitter current increases, while the voltage at the emitter, which is basically VE, which is equal to neta VBB plus VD, it decreases. Now, this is a very different kind of a behavior. Usually, we are used to the Ohm's law obeying behavior where voltage and current are directly proportional. But here you can see that current is increasing, but voltage is decreasing. So that means it is going to produce a negative resistance region in the VI characteristic of UJT. Now here I would like to mention that typically when you plot a characteristic of UJT, voltage is on the y-axis and current is taken on the x-axis. So VI characteristic. So basically here the UJT has switched from its off position to on position. Now if you see the VI characteristic of UJT, typically there are two important points. One is the peak point and the valley point. In fact, these points divide this VI curve into three important regions. First is the cutoff region, second is the negative resistance region, and third is the saturation region. What is cutoff region? Basically in this region, where is it going to be located? It will be located to the left of the peak point. Now in this region, the emitter voltage is below the peak point voltage Vp and the emitter current is approximately 0. The UJT is in its off position in this region. Now what is negative resistance region? This is the region between the peak point and the valley point. And in this region, the emitter voltage decreases from Vp to Vv and the emitter current increases from IP to IV. The increase in emitter current is due to the decrease in resistance RB1. It's due to this that this region is called negative resistance region, and in fact it is the most important region if you are thinking of applications. So for example, when the UJT is operated as an oscillator, it works in the negative resistance region. Now the third region is saturation region. This region beyond the valley point basically. So you can now imagine the whole VI curve. The leftmost region was cutoff region, then there was negative resistance region, and now beyond the V valley voltage you have the saturation region. Here the device is in its on position. The emitter voltage remains almost constant. There is a slight variation, but there is increase in the emitter current. So basically the voltage remains almost constant with the increasing emitter current. This is how you can say it. Now UJT has different applications. It can be a trigger device for triacs. It can be a non-sinusoidal oscillator like relaxation. It can be a relaxation oscillator. It can be used for sawtooth generation, timing circuits, etc.